So, good afternoon, everybody. I'm very glad to present our project that how to build an integrated and relational database for precision medicine. Since everybody here is pretty familiar with the methods we use, such as design the ER diagram and normalization, things like that. So I would like to talk more about the diagram and the motivation of this project. So bear with me with some biomedical terminology. I will try to be concise. First, the motivation of this project is we want to apply what we learn in class to solve some important real-world problems. You will see what I mean in a minute. So first, I'd like to give a definition of precision medicine. It means deliver individually tailored therapy based on the patient's disease subtype. It allows the selection of the most effective cancer treatments based on biomarkers. And the genomic testing is used widely to identify patients' gene expression profiles and determine the corresponding sensitive targeted therapy. So here is a figure to help you understand the process of precision medicine. First, we use biopsy, or currently we have another type of biopsy called liquid biopsy, which means just simply take 5 milliliters of your blood sample, and so you do not need to mess with your tumor. And then we test on the sample, either do histopathology exam or genotyping the sample. Oh, okay. So after that, based on the results of the test, we decide the best treatment for the patient. Even after the treatment or operation, we can still monitor the circulating tumor DNA changes by using the liquid biopsy. So in my understanding, precision medicine is a perfect combination of biotechnology and data science that generates actionable insights that help the patients and the doctors making decisions on optimal treatment. The advantages including avoid unnecessary treatment, reduce toxicity, and significantly improve outcomes. And also those actionable insights can also prevent, diagnose, and treat diseases. And there's potential to find a cure for currently lethal diseases. Also, we can use machine learning to predict drug response and or predict diagnosis for cancers. So I would also like to give you some example of currently used clinical genomic data tests. The first one is the Oncotype DX for breast cancer, colon cancer, or prostate cancer. So based on this genomic test results, the patient and the doctor can decide the best treatment for the patient. There's already over 1 million patients tested all over the world. And the PD-L1 expression test is for lung cancer. It's a biomarker, so the patient can decide if they need immunotherapies or not based on this test. Just this month, another paper published, they discovered some biomarkers for pan cancer. So I believe this is will also becoming standard test for pan cancer patients. Next, I want to talk about the motivation for data integration. First, currently there's a lack of integrated data source. The existing bioinformatics databases are mostly single omics, such as UCSA or PCGA databases. There's a few integrative databases such as MOPED and GTEX. They try to integrate the gene expression and histology images, which basically clinical data This is still an ongoing effort, so it's not very mature yet. So there's not many integrative data available for further analysis. Integration of multiple data sources can provide more information for more accurate clustering analysis. In a study just published this year, they integrated the clinical, genomical, and transcriptomics data and performed an integrative clustering for classifying the triple-negative breast cancers. And here is a figure showing you how we generate data from the clinical practice. We generate the molecular data, the imaging data, and literature data, clinical data, all those data, and we integrate those data and analyze those data in order to generate those useful insights for personalized medicine or precision medicine. So the approach we propose to use is build an integrated and relational database. Because currently most biological databases are in flat files, so it's not easy to integrate with external data sources. We propose to build a relational database that allows integration of diverse types of information and will efficiently manage those live data sets. Our goal is to build an curable database that we integrate all the related data in one query and can extract or subset the data for deeper analysis. Also, we improve the efficiency for storing and querying the data. There's a few challenges. The first one is the biological data, usually extremely large scale. So our solution is we just create a smaller size database to prove the concept. Here's the dramatic increase in genomic data in the past decade. The NGS technology allows the cost of sequencing of one human genome reduced from $10 million to $1,000 today. So there's enormous amount of data generated from genomic tests. The existing database SRA grows 10,000 times during the last decade. You can see in 2009, there's only one, the size is only 1 terabases, and in 2019, there's more than 10,000 terabases for this database. So another challenge we have is due to the privacy concern, it's hard to get access to patient genotyping and phenotyping data. So we use the simulated data. And in addition, there's various non-trivial data types of biological files. Also, biological data has extremely flexible schema, which makes the normalization difficult, but we are trying our best to normalize those data. The method we use is first we design the ER diagram and we normalize it and we determine the entities. Then we use DDL to populate the database, and then we use DML to manipulate the database, extract the data, etc. So I want to talk a little bit about how I simulated the genomic test results data. It's basically based on the widely used HER2 score to stand for the expression levels of HER2 gene expression. So I generated a metric of random number from 1 to 3 to represent the genomic test result. Here's the ER diagram of our database. We have a table for biopsy data, for phenotype data, genotype data, and we also have a gene information table to, it's kind of a future proof, so we can connect to outside databases. So here's a demonstration of a simple SQL query to extract data from our database. We join some table, and then with some selection criteria, we extract some data and group them and order them by some sequence. So Liang, do you want to start?
Yeah, sure. So this chart will see the this is an example of the patient data that we have today. So it has the patient ID, the diagnosed result, and all kinds of variables that we have available in this data. Next page. Next page. Yeah. Here I run a logistic regression stepwise selection on this set of this data set, and we picked these algorithm picked seven variables that is being used to do the as a training data to predict the result. As you can see in the classification table, the accurate, the correct percentage is at 97%. Next page. This is a scatter plot of the chosen 7 parameters. Usually, when we view this scatter plot, you can get a sense of the correlation between the variables. Next one. Yeah, this is another one, scatter plot with the histogram of the variables. So we can see that mostly they are in like normal distribution, except the first one. So. And also, we are able to build a REST service on one side, and then use the post from the postman or from the browser to send the request and be able to using the patient ID and to query the database to get the original data, and then we apply these trained model and then get the diagnosed results and send back. So this is a code for that. See in the middle, go back please. In the middle, you got the highlighted area is the where we load the training model here. So next page. So this is running screen where we run the main Python, and then in the bottom of this page you can see that we are posting a request for the patient ID 86355, and this is the display that is shown on the main side. Next page. This is a request side. This method is post, and then because we're running on our local machine, here's the this is function get breast cancer diagnosed, and slash number is patient ID. You can get the response from the REST service that the predicted diagnosed feedback is M. So we were able to do that by providing different patient ID. You can get the diagnosis. This is a modeling side where we train the model, use the existing data, and this is the data set that we train our model from. And here is the training part, and at the bottom we save the train model to that pickle format. So next page. Yeah, conclusion, Lei.
Okay. Yeah, so the conclusion is we successfully designed the ER diagram and populated the database, and demonstrated the extraction data from the database using SQL queries. And also we built an online prediction platform for breast cancer diagnosis. As you see in this figure, there are three parties: the doctor, the patient, and the data scientist. They can all easily retrieve data from the database and perform analysis of those data. Also, our database is a real-world application of the database knowledge we learned in class, and it also shows how data science helps generating value from data. So next, we propose, because for real life, the genomics data are quite large, like maybe we need to utilize cloud computing such as AWS or Google Cloud Platform. Maybe we can get some help from our last group. So we propose to build a cloud-based auto deep learning platform for integrative analysis of NGS, WES, and clinical data to predict the subtypes of cancer. And also, we can also integrate data from more sources, such as proteomics data, or we can record the environmental factors for the patients, like their diet type and exercises habits, to give a more dimension for our analysis. And in addition, we can connect our database to outside databases, such as TCGA or GTEx, as I mentioned. Last but not least, we can create a time series database. Because the liquid biopsy technology, we can easily monitor the circulating tumor DNA change. So we do not need to get tumor sample every time. We just draw 5 milliliter blood. So this makes it's very feasible to create a time series database. So we would like to thank James for the preliminary work, and we would like to thank Dr. George Bell for giving us initial guidance for this project. And we would like to thank Dr. Engels and all the students for the semester. Yeah, thank you.
Very nice question.